Knowing that there are a lot of technical people here in the room, I normally like to do a small presentation and do sort of like a vibe entry on how to develop wind farms. So we heard a lot about wind resource here today, variable distribution, measurements, etc. But what do we do exactly with all those data sets? Now, we at Youwind, we basically make sure that we capture the data sets and we calculate the P50, the P90s, but we calibrate everything together with cost items. So before I start a presentation, which I'm obliged to do for my commercial team, obviously, basically for commercial purposes, but knowing you're all technical people, I just want to show you a little bit. So how do we do this normally? Just as a very brief presentation. And I would invite all of you actually to contact me here after this presentation to have a live demo on how this works in your own wind farms. So basically, the way that Youwind works is essentially we combine mapping, GIS data, we combine electrical models, and we combine financial models into one platform. So as easy as this, you have everything in one place. But exactly the main difference this with normal applications is that with a click of the button, you basically have all the information from wind data to elevation data to bathymetry if it's offshore to essentially what is my levelized cost of energy and what's the profit of the project. But before I show you these details, I better show you a small presentation. If not, I will have the commercial team will have my head, essentially. So basically, what I want to explain today is what is Youwind is about and how we go from wind resource data to optimized layouts, to optimized yield and LCOE. And we're going to make a scenario analysis both for onshore and offshore projects. And we're going to do this also with storage. I don't know how many of you are familiar with the BESS optimization that we have at Youwind, but I would like to explain a little bit how this works also for wind datasets and not only for solar. So I'll just explain a little bit who I am and what Youwind is, and then we're going to deep dive into what is a process of a techno-economic assessment of layout design and LCOE optimization, followed by introduction to battery energy storage systems, and we're going to then have offshore case study and an onshore case study in the Philippines about that. So a little bit about myself. My name is Edvald Edvaldsson. I'm the founder and CTO at Youwind. I'm a mechanical engineer, master's in wind energy engineering. I started my career actually in a different setting, actually in banking, working in risk management. So if ever you think that sometimes wind resource assessment is boring and you feel like changing profession, don't go to banking. I assure you it's more dull than wind energy engineering, despite the contracts. So then after working for dreadful 2 years in banking, I went to wind energy engineering and was working mainly in a developer in Denmark called Ørsted, and then in Spain for Iberdrola and other developers as well. So I'm essentially responsible for the design and the operations of Youwind. And what is Youwind essentially? So Youwind is basically a web-based platform. So it's a platform that is basically in the cloud. It's designed for both onshore and offshore projects. And the idea behind Youwind is essentially to gather GIS data together with financial engineering, wind data, and the full optimization behind how to go from really raw data sets into an optimized wind farm. We wanted to make this as easy as possible, and not only just to say that offshore wind consultants would be obsolete. On the contrary, you normally know that when you're looking at offshore wind projects, there are many iterations. You have 50, 60, hundreds of iterations normally when you're looking at projects, and then you need to look at the other sides. What Youwind does is it enables experts to do these simulations at a very high pace. So you're able to focus on the details where they're needed. So the real analysis where you see some uncertainties, you see some anomalies, and you want to really analyze that in more detail, like we hear before explained here by Mark McDonald. So it's all expert backed. So we're all wind energy engineers, and the results from Youwind are essentially bankable, meaning that the process has gone through several financial lenders advisors as well. So the idea behind Youwind is simple. you start with an area. So how do you go from area screening to a fully bankable yield assessment? So you start out with saying, I have a very large seabed or a land area as well that you want to screen. And you basically say, I would like to see where is this more interesting for me to place offshore wind turbines. So we make LCOE heat maps. So we simulate exactly the heat points on where is it interesting to add offshore wind farms. Then we go into the details of the wind resource assessment. So here you can add the data sets that you have from Vortex. You can either upload your own as well. You can do measurement campaigns and do full validation within the platform. And then everything is combined with the validated wake models and layout optimization, taking both internal wakes and also external wakes into account. But it's not all that, because it's only a part of the story if you have the wind resource assessment and the layout design in place. How does this combine with costs, and how does this combine with electrical systems? So electrical system design is basically thought through to be a fully optimizer that basically makes sure that the layout optimized is also connected together, and you get essentially the full development as needed. And as a summary, you get really reliable P50, P90 analysis. So we calculate also the uncertainties, not only for the wind resource assessment, but as Youwind also calculates electrical losses, it also calculates unavailability of turbines. Then everything is sort of combined into one place and essentially with one click. So today we're going to talk about analysis we have done here in the Philippines with Vortex data. So I assume you're all familiar with the Vortex data maps, and Oriol and Marvin were nice enough to share some data so we could do this analysis sort of in more detail. So we're going to look at an area in the north in the Philippines. So it's an area that has been a very high interest for offshore wind, but also an interest for onshore wind. So it's actually a very large area that is interesting to analyze in more detail. So what is actually a good wind site? So we talked about area screening. We talked about wind data sets. We talked about should it be windy or not, frequency distribution, etc. But it's not only wind that needs to be there. The project needs to be buildable, connectable, permittable, and easy to finance and easy to operate. So the site conditions, essentially, they drive the cost and risks. So for onshore, you need terrain, access roads, logistics, you need foundations, you need to evaluate visual impact, grid connection. For fixed offshore, you need to make sure what's the bathymetry, so what sort of technology do you use? Is it a monopile? Is it a jacket? And how much does this foundation weigh as a function of bathymetry and soil conditions? And then what about floating? Seabed slopes is also very important. How can you make sure you have the right technology for the right site that you're looking at? How do dynamic cables with export and array cables work? And what is the port strategy? How do I find the right ports into the analysis? So the energy yield is essentially the key here. So it drives the commercial foundation, but with wake losses, layout, availability, measurement strategy, these all influence what is the LCOE analysis of offshore wind farms and onshore. So we start up with, let's say, the process of techno-economic assessments in LCOE optimization. And this is a very typical path that you look at, not only in Europe, but also in Southeast Asia and in Japan, for example, where I'm just recently coming from, that shows essentially you start out with some seabed areas and you look at what are available government designated areas for my sites. So then you look at what is the wind resource. To start out with, normally, well, as we always recommend to use the Vortex data to do the analysis, is to look at what is the wind data at my site and what is actually the distribution of this wind data. So I don't need to go into what is the power law of wind power, but I need to go through this also with, let's say, the non-experts. But essentially, as wind speed is in the power of 3, then only the slightest difference that you have from your average wind speed has a massive impact on your power output and hence your business case. So for offshore wind, we look at also bathymetry. So here with Youwind, you basically filter out what is a site, a suitable area for fixed bottom, so basically monopiles or jackets, and what is a feasible site for a floating one. So here you can basically filter out with wind data, what is the bathymetry, and where do we actually match from the overall design to fit this into a particular project. So we start then with the next path, which is the soil structure. So it's not only enough to have bathymetry, you need to know what's below also. So is it a rocky seabed? Is it muddy? Is it very sandy? This has a massive impact on the cost of your foundations and will decide if it's a project viable or not. And then the second or the fifth part, essentially, what is the grid connection? Is there a grid connection? How far is the harbor to do installation? How far is the harbor to do O&M? This is all extremely important to know. How does my wind farm yield, but also how much does my wind farm lose from the yield part of the turbine into the actual grid point? So this is extremely important also to simulate in as well. And then to go over the details of offshore logistics, well, these are complicated machines. They're operating at sea. It's enough that offshore wind is complicated, but it gets even more complicated when we're dealing with floating structures. So this is also the other barrier that we need to go through. I really enjoy also showing these graphs. I only have one equation in this presentation, so bear with me with a couple of graphs. So this is just to show a little bit how the difference between costs of fixed bottom offshore wind plants together with floating offshore wind plants works. So essentially, when you're looking at these systems, the turbine is a very small part of it. So it's very different from onshore wind, essentially, where you have the turbine probably 70, 80% of the overall cost. But here, with the difference between the fixed bottom and floating is that the main difference is that the substructure of foundation is so much higher in proportion with the overall LCOE that it's a very important part to look at what are my site conditions at each area. So I've been saying LCOE for a long time and say it quite often in this presentation, but what is LCOE? So levelized costs of electricity. So it's essentially the net present value of total cost over the lifetime divided by net present value of electrical energy produced over the lifetime. So it's a metric that calculates what is the cost of this particular wind farm in terms of relative cost of installation, procurement, and operations and maintenance, but together with how much it's going to produce over the lifetime. It's a metric to explain and to show what is a good site versus a bad site, and is this site actually profitable or not? Now, it's extremely important to mention also that wind resource, although this is a wind resource workshop, is not only the most important thing. So there are two factors that are as important as a normal capacity factor for a project, which is, first of all, WACC, which is the cost of capital. So how much debt, how much equity, how much does it cost actually to get? And what happens if these values change? So as you can see here, if we take a base case of a particular offshore wind project, let's say 3.5 million per megawatt, you have an LCOE of, let's say, 86.8. So what happens if CAPEX increases? If CAPEX increases 40%, you see here that the LCOE jumps up 115. Now, what happens if LCOE increases? Let's say from 7 to 14, which now maybe is not really unrealistic given how the landscape is in the financial world. You see that then the spikes is already at 142. So it's extremely sensitive not only to wind data, but also to financial terms like weighted average cost of capital. Now with Youwind, you can basically go into these details and look at what is the process of techno-economic assessment and an LCOE optimization. So if you have a large seabed, if you're looking at offshore wind farm projects in Thailand, in some areas, you can simply draw or upload a polygon. You can split it up into very small areas. This depends on the grid that you have for your wind data. So if using Vortex Farm, for example, you can actually split this up into 100 by 100 meters. And you can go per site and look at what is the bathymetry, what is the wind data at each location, and how far is it from the grid connection to figure out what is my overall LCOE at each location. And here I can basically filter out what is my cost of energy for this particular area, how big is it, and how many turbines can I install. For onshore, this is also the same. So this is a typical site that we have, for example, an area in Spain. So here you lay over in 3D your grid map, your farm map, your WRG file, and you basically say, find me the best area within this zone, see how many turbines can fit, and then optimize that in terms of finalizing the layout design to minimize wake losses. Now, what are wake losses? So it's something very important to mention also that for offshore wind, wake losses are very relevant because you're dealing with very large clusters. It's not only the internal wake effects that we need to analyze, it's also the neighboring wind farm effects. So if you're looking at project in the North Sea, in Germany, for example, you have thousands of neighboring wind turbines, and you need to figure out what is the lost energy related to these turbines. So here you see a simple wake visualization of a wind farm in the Netherlands, where basically we're calculating from a given wake model what is a potential loss on the energy as if we already have the given wind data. With the loss extraction, we can then say we have an optimized layout, and I will always say that an optimized layout deals with looking at what is the cost of energy at each location. But then we need to go into what we say this LCOE optimization, which is also making sure that the cables are connected with the shortest distance, and we evaluate what is the cost of energy when we're looking at what is the exact given scope of my electrical setup. Should it be offshore substations? Should it be 2 offshore substations? Which sort of cable should I add? What sort of cross section should there be, etc. And of course, for onshore, we need to evaluate this with the environmental impact. So what is the noise level of my turbines? What is the visual impact? Is there a shadow flickering? And what are other restrictions I might have? Where are the roads connected? And where's the grid as well? All these items come into play. We're essentially trying to summarize these techno-economic assessments into the daily and seasonal variation of the production together with the annual energy production. And this all comes to play, just to summarize, as we're talking about wind resource today, that we now, with Youwind, we gather these data and we convert them into a knowledge where we not only are calculating the yield, but we're connecting it to the cost elements as well. And with that, cost elements are maybe not really realistic unless we're dealing with hybrid systems. So this is one of the key elements we have been presenting now in Southeast Asia, which is essentially that you can simulate what is the benefit of a BESS system together with my either existing wind power plant or solar plant, or if I would do a repowering at the exact site. So this is just a visualization that you can see that also works inside the platform, is that optimization on how many units can I place? What is the economic benefit if I still use the roads, still use the cables, and what additional cost do I have to use and add for the BOP? So to summarize, so the process of techno-economic assessment in LCOE essentially screen, optimize. Optimize means essentially where do I place the turbines in the ideal place? So how do I use these wake models and these economic assessments to make sure that the locations on each turbine and which turbine to use are ideal? And then you simply go into the detailed design. So which turbine is better for each location? The distance between the turbines, the distance between the neighbors, and how far these elements are from essentially the grid connection. And then finally, you can decide, so what is the ideal element? Because everything is connected in terms of cost. So if you move a turbine that goes from -15 to -20, the calculation continues in a few bytes a seconds to say what is the updated cost. So is it worth it to move the turbine towards a windier area where you have deeper waters, or is it not? So the efficiency of offshore wind farms is not only wake losses, internal and external, it's also electrical losses, it's turbine performance, it's environmental losses, it's curtailment, operational losses, and availability. So what we wanted to do with Youwind is to have everything in one, essentially. So you don't need to start saying the wake losses, what are my curtailment strategies. If you have everything defined into one area, by having a duplicate of your project, you don't need to start all over again. And this is basically what we wanted to highlight as one of the key elements of our platform. So we're looking at efficiencies. So we need to look at wake losses, so wake effects. I'm sure you're all very familiar with the wake effects. And these are essentially one of the elements that we, at least for offshore wind, we need to make very detailed analysis of, and to analyze them also into different wake models. So you all know basically that wake models many of them have been validated, but there's not really any process or any sort of consensus as which wake model is more efficient than the others. Some are more efficient in Southeast Asia, some are more efficient in very large clusters in Germany, for example. But we basically want to make sure that these wake models are simulated into detailed order in the platform. So the wake effects, yeah, it's a very famous photo. So essentially, the wakes are visualized like this. So the first row is hitting by the winds, and then essentially you have a deflection of wakes. So the second row gets lower wind speed than it should. So the internal external wake losses, as I mentioned before, are extremely important. So here is a site that we have in the French Mediterranean and the Spanish Mediterranean, just to show you that even though you're doing planning of large wind farms, and this might be very relevant also for offshore wind in Thailand, is that when you have large clusters of neighboring wind farm effects, they will also have very long wake tails, as you can see here, that comes and will have an impact on your current analysis that you're doing here. Here, these wind farms are approximately 80 kilometers apart, and they have around 1.5% loss on this current wind farm here in the Spanish region. So it is very important also for the early stages to simulate these impacts. But wakes are not only losses in energy; they also have an impact on the turbulence. So wake added turbulence will have an impact on which turbine is utilized and what not. So this is also something that we wanted to do from beginning, is to have turbine site suitability also included in the optimization. So how close can I actually have the turbines together in order to make sure that they are actually viable to be built or not, and which turbine is available. So here is essentially with every iteration, with every calculation, we calculate what is the exact turbulence TI class of the turbine, and what is the mean TI and the effective TI at the rated wind speed when we're doing these analyses. To add a layout to a wind farm is relatively easy. You simply say and look at the area that you have, how many turbines you want to add, and it's relatively easy to add these turbines to your layer, and to visualize that is quite straightforward, and also to calculate wake losses. But what about optimization? So one of the key things that we need to do when we're looking at optimization is to look at what is a global optimum for optimization of wind farms. The global optimum needs to go into the details of looking at how do I make sure that I reiterate these layout designs to make sure that is fully optimized, and I don't need to make sure and I don't need to run it again for a different item. So what we developed is actually a generic algorithm. We call it LOGA, where we actually mutate each location of the turbines, and we produce thousands of layouts, hundreds and thousands of layouts, where we each make sure we're moving the turbine on different locations, and we reiterate what is the gross production and what is the net production. This also has an impact and has a meaning when you're looking at, if you have a grid file, for example, a WRG file. So on each and every location where you move the turbine, you can also simulate what is the exact production and what is a potential output when you have these free placement. This also works when you have a time series and you're using a map or farm that you're doing the horizontal extrapolation. This also works in that part. So from the measurement points into the exact grid point, you can also simulate this, what is the exact improvement. And we estimate here more or less here between 1% and 3% improvement. And from here, you basically go into the process of techno-economic assessment that includes the optimization on electrical design. So we also need to, we can't only optimize where the location is for the offshore substation, we also need to optimize what is the shortest distance when you're designing the arrays and which cross-section should you use. So for each iteration, we also calculate the kilometers that you have for your cables, and we also calculate the losses that you have through the cables, the losses and the actual availability that you have. Because transmission availability, it also has a very big impact on failure rate per kilometer. You have repair time, and then you have some statistical combinations that you might have a risk for when you're doing these analyses. And this is one of the items that I wanted to show that we are working on currently in a joint program with which we call Sudoku, that we're working with DTU and other research institutions in Northern Europe. Is actually a wake steering control optimization. So if you look at wake steering, it's essentially what I showed before, where you have wakes in the second row of your wind farm. What we call wake steering, it means exactly that we look at the TI values, we look at the inputs that you have, and we simply yaw the turbine a few grid points. So we essentially make sure that the second line has less deflection on the first row, and this means also that the first turbine will have less power. But in total, we're looking at the overall wind farm. The overall wind farm will have a higher AAP. So the second and the third and the fourth row will then mean they have more power, more AAP. And this essentially means that you can play around with these control features to optimize what is a potential gain for your wind farm. So it's a very interesting project and has already given some benefits for some projects. And it's one of the key items that we have for wake deflection and wake control steering. This is a small summary of some wake models that we have, both for onshore and offshore projects. These are all wake models that we run in Youwind. The good thing about Youwind is that you run them all at the same time. When you run them all at the same time, you don't need to press start and then wait until it finishes and then change it and then start it again. We run everything in the back end as is a web-based solution, so you can really say, make me 3 different, or make me 10 scenarios with this capacity, change the turbines to these turbines, and then calculate all the wake models at the same time. And it will simply do that in a simple order in the web-based platform. Now, I don't want to go into too much detail here. Also, it's close to the afternoon, and I don't want you all to fall asleep in that detail. But we do have some inputs here on, for example, 2 very interesting wake models for offshore, which is the Turbo Park, which has been validated quite rigorously in the German North Sea for very large clusters. And then what I was actually introducing now in Japan, which is the Blondell Ishihara wake model. So both essentially depend on TI and CTs, and are actually looking at the Gaussian velocity deficit, or basically the Gaussian superposition at each location. So it's a quite an interesting method. There are some validations you have here, but then you have also the usual suspects, which is Park 2, eddy viscosity. You can use large array corrections, or you can simply use the ones that I just mentioned before. So I won't go into too much detail into BESS, battery energy storage systems. Maybe you're not so interested in those items, but I do want to explain a little bit how they work, because they are getting more and more important for projects, both for onshore and offshore wind, but also for solar. And the best applications, most of them come from solar. And we felt that there was something needed that combines solar, wind, and looks also at the optimization that we do at Youwind for onshore and offshore projects. So what we wanted to do was to combine the time series that we have for production, so the power output of your wind design, with an optimizer that looks at sort of this co-located business case. So it's simply what we have is a layout tool where we look at different items. So the first, you have BESS library items such as turbines. So you basically choose which BESS unit should I use, which converters should I use, which inverters, and how to actually rack these items into one simple layout as you would do with a turbine layout. So it basically looks like this. You have an area and you simply say, maximize this area that I have let's say this area is from a landowner, and you want to see how many units can I place. And it's simply, same as for the turbines, it optimizes how many units can I fit, and where will they be placed, and how much will it cost to have. So the layout generator basically, it looks at regulation constraints, exclusion zones, which is basically protected areas. It looks at required access roads, access in the buildings, fire hazard implementations, and maybe it could also look at some flexible shapes of different buildings. And the generator basically takes these constraints into account. What are the exclusion zones? What is the provided road access? And if there are any exclusion zones, it will also take those into account if you have a building, and maybe some other restriction that needs to be accounted for. So yeah, you can draw the best units. It's also actually quite fun to do. Some people ask me or tell me that they can't even believe they're paid to play around in the system just to optimize some layouts, but that's another part. But here I wanted to summarize. So when you're doing this co-located optimization, you're simply looking at what is my power output. You have some solar production, wind, you maybe have some export that you're looking at the grid profile. And then what is a potential curtailment that I might have? So the curtailment is getting more and more popular now. In discussion, we're looking at where can I place turbines and what is the viability of my project. So if the project is curtailed, what potential revenue increase might I have if I would have BESS? So we look at the power prices, we look at if you have a PPA as well, you can add those to the system. But then you can also simulate if I have a curtailment, what sort of impact does this have on my business case? So it was a very large introduction to the case studies. So I'll also go through those just maybe a little bit in more detail. But if we look at the case studies, the introduction is important because this is one of the things that we do normally when we're looking at offshore wind farms. So if you're an advisor or if you're a developer, you might get an area sent with a shapefile, or you're looking at an area where is the grid connection, and what's the first thing you do? Well, you need to upload that into a system, and you need to find out quite fast what sort of details do I need in order to continue the analysis, and what do I have when I do the simulations. So we have everything combined into one area, because with a symbol of the button, you can basically here, and this is the northern part in the Philippines, you can basically see what is the bathymetry. So what's the bathymetry level, and what sites are suitable for fixed bottom, and what are suitable for floating. So the purple area is for fixed bottom, and the pink one is essentially for floating. And what I want to show here is a simple analysis that I did just now by saying, what happens if I have a very large floating wind farm versus a very small nearshore wind farm? So I simply make a small filtering exercise. So I basically take the big polygon, and it has an area from 86 to 300 meters, which is quite big. And it has quite a steep fall down in the bathymetry, which means that it might have an impact on choosing what sort of anchors I have for the floaters. And I want to limit this to a particular sub area. So I simply say, find an area between 86 and 300. It will filter out this area. And then you could also go into the next part and say, add me a layout to this area. So I can simply say with the layout optimizer, by defining which type of foundation, I can say I would like a semi-sub with this sub area and this bathymetry, and a spar buoy for this bathymetry. And the optimizer and the layout generator will simply differentiate between type of technology, how many mooring lines, what's the connection point, and essentially, to summarize, how much will it cost when I have this. So by applying this to this area, I simply say I have my viable wind map. So I actually have the wind resource grid file from Vortex. I'll show you also how that works with a time series that I have for the exact site. But when you're doing the early stage screening, it's not so relevant the exact details of wind resource if you have a good farm or grid file. That's basically also always the conclusion, because it could be that some areas could be moved and could not be moved for the wind resource. But the idea is that when you're first looking at the area, is you're trying to shape the area in terms of finding the best areas for the wind data. So here you can see basically here's the wind map. It is a Weibull distribution. It's quite a high wind area, but it's quite steep as well, which is quite representative for this area of this part of the world. So we can then look at how do we take this site. We can look at the windrows, and we can look at how do we optimize this site for being a completely gridded file to a fully optimized layout. This might have an impact also in the early stage, because it's not only the filtering of the areas itself, it's trying to find out how much energy can you extract if you have the optimum placement of the turbines. So this is the max AP optimizer that I showed before, how it works with the logo optimizer, the generic algorithm. It simply takes exploration steps. So we start with rotor diameter spacing of 6 times the rotor. We mutate the shape of the layout as much as possible, and we look at the windrows, and for each spin we calculate what is the gross and what is the net area for here. This, you might think, might take a few days. This takes less than 2 minutes with our optimizer running, and it has an increased AP of around 1.3% when we finalize the design. Now, if we look at some other parts of this, we might also want to think at what about LCOE? Well, we have now maximized the turbine locations, but what about connecting the turbines, and what about finding the areas that are more suitable not only for wind but also for bathymetry? So here we run the same optimizer, but now for LCOE. So we're maximizing the net AP and minimizing the LCOE. So we're looking at bathymetry, we're looking at how far each position is to the offshore grid point, and we're looking at how can we place the turbines in an area while making sure that the yield is high enough to minimize the electrical losses and the electrical distances. So here you can see same distance, but we're running from looking at an offshore project here from 121 down to 115. So we're actually having an impact on, we're taking a small chunk of net AP to balance with the overall cost of your project. So here you have a full optimization, essentially net AP, including the cost, and everything is connected in these regards. But what about some fixed bottom areas? So looking at the same sites, we can see that there are not a lot of areas that we can place fixed bottom. And actually, for some areas, we can only place 4 turbines. But maybe that's not really the biggest problem, because we can still look at 4 turbines. These turbines are massive. 4 turbines of 15 megawatts will give you a lot of power when you're running this analysis. So what if we do the same thing? So we're going to look at 4 different turbines. We're going to run the LCOE optimizer, and we're going to look at how much does it cost. If you look at the LCOE perspective, if I just place the 4 turbines here, I connect them to the grid point, and what happens if I do the optimization? So same here, LCOE 87 to 82, so a relative increase in the yield. But you can see here also how the turbines are placed. So not in the center, because by looking at the windrows and by looking at the exact grid point that you have the gross production, but also the net production when you're running it through the wake models. So offshore wind project, 400 megawatts, 120 euros a megawatt hour, 4 turbines, 82. So you can also see that there's a big difference also when you're looking at, it's not everything is a economy of scale when you're looking at these projects, because obviously floating offshore wind is a massive capex heavy industry. And also what we're looking at for the Philippines, that there are not a lot of offshore fixed bottom projects. So perhaps that could be the way moving forward. But for this project of fixed bottom, let's look at an area next to the grid point. So can we actually add here a storage BESS plant? So we run this to the optimizer. We're looking at how much are we producing. So we're looking at now a time series to say, if I place a time series here, I run it through the calculation. And if I just draw an area here next to the grid point, how many units of BESS can I add? So this is essentially the results. So these are an optimized figures here, especially suitable for the Philippines, because in the Philippines, you have a minimum requirement of storage for your projects. And essentially, this will fulfill those requirements, because you can basically do your analysis and design in one place. and in fact with only one tool. And this is essentially the combined function. You have your 4 turbines. They are connected with one string into your onshore substation that is then connected to your BESS unit. Now, this is also possible to do with a full hybrid system. So if you have a solar plant as well. So by uploading the power time series of your solar plant, and this you can do from known systems like PVSys or any other PV design. By uploading that, you simply have what is the total power time series of your solar system. So by looking at this, you can then make a full detailed optimization on a dispatch optimizations, as we call it. It takes into account what is my price during the time of the day, what is an interesting day in the year, and how much do I generate through the time as well. So as you can see here, what is the uploaded, what is the wind data that is producing, what is the state of charge of the battery, and what is the potential day ahead price that you have here. And you can look at basically a calendar if you're looking at in hindsight, what is a good data sets to look at when you're doing this optimization for your projects. So this is just to show a little bit that, you know, the coupled hybrid system is also very important to look at when you're looking at offshore wind projects. So we're looking at onshore projects. Now, this is where the fun stuff starts. So same area. Looking at here on the left side is the vortex map that you have, looking at where the wind data is very high here in the red, is quite high where the area was. We're looking at floating projects, but also here in the eastern part, essentially more detailed around this area here that we're going to look at in more detail. By looking at the map of Youwind, we see also where there is a time series that we can use to do horizontal extrapolation to each turbine location. And we can also add here a layer, which is restrictions to the layout design, which are, for example, grid connection. You don't want to build too heavy of a grid connection. You want to stay relatively close to those. Where are the roads and where is there a harbor, actually, to have the turbines as a fitting to my logistics center. So what we do here in the first part is basically the screening. So you can simply draw a very big polygon on where the area is, where the wind speed is the highest, and you can filter out on different items. So you basically say, I don't want any water surface. I don't want any water areas. I want to be far away from bridges. I want to make sure that I'm at least 30 or 100 meters away from buildings. And I don't want any foresty areas either, if you're looking at very detailed analysis. Then you can do something which is quite cool, which is basically you can cut this area out of your polygon. Basically say, this is not a part of my analysis anymore. I just want to place turbines, ideally, where the wind speed is the highest and the cost is the lowest. But I also take into account other restrictions to my layout. So here I can basically say, I'm removing all these areas, but what about slopes? So here you have essentially a range filter of slopes where you can basically say, remove the slopes that are higher than 12 degrees and then redesign the area where I can place the turbines, ideally taking these restrictions into account. So then you just redesign the layout. You make sure that you're looking at an idealized layout where you're taking into account the distance to the grid, but you're looking also at the grid file. So you're looking at where the wind speed is the highest, and you're still looking at how many turbines can I place in this phase. Here you can do also saying, basically apply these slope ranges, and then basically the redesign will also make sure that these slope ranges are excluded from the optimization, and then you have a fully redesigned polygon as well. Now, this is just the screening phase that I'm just explaining, and this is very common when we're looking at, are there any areas of interest? And this is very much used when you're looking at different areas, also in Thailand that we learned here from some developers that are looking at projects. Where do I start? Where are the interesting areas? How far are they from the grid? How is the wind resource? And how many turbines can I place if I take all these restrictions into account? This is the type of answers we want to give to the users here. So essentially, we take out all the restrictions, we take out the slopes, and now I'm redesigning the layout to basically, under restrictions on distance between the turbines, how many turbines can I place into this area? Now I have placed some turbines in the area. I've just in the first phase just tried to maximize the distance between the turbines. But what happens if I then run it into the layout optimizer looking at the exact wind resource? As you can see here then, the same as before for the floating and the fixed bottom sites, there's a relative increase here when you're looking at both time series and a WRG file in the optimization. And as a result here, if you run this for a time series, and this is a typical one that you will see in this side of the world, where you see essentially what is the wind farm power output by wind speed. So this is a 10-year time series that we had for this area. And you can see here some anomalies that you see here from the power curve, which is coming from a different sector. And this is essentially one of the areas that is coming from the shore that sees some of the anomalies that the power output is really affected by wake losses in the big wind farm. The daily and the seasonal variation of the production is quite interesting as well, where you have the highest production essentially here in these in the winter months that you have here as well. Then environmental impact studies. So how far away can you see the turbines? Quite important as well. Also, when you're looking at these analysis from the early stage. This is a very quick analysis that you can do. So how many turbines can be seen on each location that you can do and visualize. You can then jump into saying, so what about shadow flickering? And what about some restrictions and curtailments I might have if there are very detailed shadow flickerings at each area? So here you can basically look at the topography of the area. You can look at how many hours I might have from shadow flickering, and you can go into more detail on seeing which are the areas that are more sensitive than others. As you can see here, there are obviously some areas that you can do and might have an impact on some changes of the layout, which are beyond the optimizer as well, and you can then add them as restriction to your design. Noise studies as well. Obviously, different turbines have different noise curves, have different frequency levels, and this is also one of the motivations for having everything done in a fully simulation at the same time with Youwind, is because if you're looking at a turbine that might have a higher power output versus a turbine that is lower in frequency, you might have a different impact on the business case that you're looking at. So by comparing these items, it's very easy to say what sort of interest you might have for the optimal design. And to wrap up with a few items here, which are also quite important, is civil work. So do I fit in the turbines? Do I need to build in more roads? How many kilometers of roads do I need to build? Where are there access points to the design that I can place? So this is just a very easy filtering out sort of how many turbines can I place, how many roads should I build, and essentially how many cables should I build. So this is just a cable study here. How do I connect the turbines into the collector station here, our minimum onshore transformer station, to then connect to the grid? And as I said, everything comes with a cost item. So by moving the turbine, you move the cable, you move the road, essentially has an impact on your cost items, not only for the yield part. And then this just to show how everything sort of comes to place. Some are restriction areas, some are not. And these are one of the things that you can do in the exclusion zone, is to filter out these areas into more detail. And here, this is the study that we just wrapped up in showing and exercising, and actually just summarizing here today. Where do I fit the turbines? What are they yielding? And then finally, how do they look like? And funny enough, that this is actual wind farm that was built earlier this year in this region. So this is just to show a little bit how you can do the filtering, add the constraints you might have with the correct wind resource data that you might need, and then basically optimize and filter out what are interest of projects that you might have for this. I hope it was a lot of information, and I hope it was useful, and happy to take any questions, or if not, I can also show you in a live demo how this platform works in reality. Thank you very much.